So in this video we will be discussing about the introduction to the design of water tanks. Introduction to the design of water tanks. So first of all, let us discuss about the classification of tank. The tanks can be classified as that which is resting on ground, or that which is elevated, or underground. It can be classified based on shape, as again circular, rectangular, spherical, inch, or circular with conical bottom. So in the coming videos we will be discussing on tanks which are resting on ground and those which are circular in shape and rectangular in shape. So in the coming videos we will be discussing on the design of these circular and rectangular tanks with different joint conditions. So for the design of tank, the code that which is used, second one is the IS code. So IS 3370 is used for the design of tank. It has 4 different parts. The first part is about general requirement. Part 1 is about general requirements. Part 2 is about RCC. Part 3 is about piece test. And part 3 is about design tables. So both these codes are of 1967 published and this 2009 published. Coming on to the essential requirement of any water tank. Essential requirement of any water tank. Any water tank shall be designed such that this water tank is impervious, or the permeability is absolutely 0, so that there is no leakage, or the tank should not be porous in nature. The fourth one is about the cement content. The minimum cement content is given as 320 kilogram per meter cube. 320 kilogram per meter cube of concrete as per IS 3370 part 1. This is part 1. So from now onwards I am not writing IS 3370 because this is entire thing is based on 3370. This is based on part 1 and it is given in table 1. And the maximum cement content, it is given as 400 kilogram per meter cube in order to prevent the effects of shrinkage. This is given in clause 5 of 3370 part 1. Then it's also given that we have to use a minimum grade of M30 concrete if we are dealing with RCC water tank. For RCC water tank, minimum M30 grade should be used. Although we can go for M25, but mostly we are sticking on with M30 concrete. The fifth condition is about the cracking that that any the cracking requirement or the design consideration. Okay, the design consideration. Here we are here in the design of water tank. We are designing such that there is no cracking in concrete. Okay, and the code is giving us the various methods to prevent, various methods to control crack formation, and that is given in clause 8 of part 1. Okay, clause 8 of part 1. There it is given as correct placing of reinforcement, the importance of small size bars, the usage of deformed bars, then avoiding the use of thick timber sections as shuttering, which essentially prevent the flow of hydration heat of hydration, and also about permitting some expansion and contraction through proper disjoint detailing, and even the code is specifying the minimum curing period for water tanks as 14 days as per clause 8.2.4, and also the rate of filling these water tanks shall be at about 1 meter height per 24 hours, and that is given in clause 8.2.9. So coming on to the sixth point that we are going to discuss is the general design consideration, general design requirements. So in general design requirements, this is entirely based on part 2 of IS 3370 2009. Here we are going to see some important things that we are normally using in our design procedure. The first one is the permissible stress in concrete. Permissible stress in concrete. So there in table 1, this is given in table 1 for resistance to cracking case. Okay, it is not for strength calculation, it is for resistance to cracking case. It is given in table 1. So for different grade of concrete, what is the maximum permissible direct tension, and the tension due to bending is given in table 1. The second thing we have to look into is the permissible stress in steel. This is again given in table 4. This is given in table 4 of IS 3370 part 2 2009, and this is for the strength calculation. There we can get the different values of sigma st for mild steel and HYST bars. Okay. Then in general design requirements, it is very important to look into the steel reinforcement ratios, the percentage reinforcement. The reinforcement percentage. This is given in clause 8 of 3370 part 2, clause 8. There it is written as in case of wall, floor and roof, in each of the two directions, in case of wall, floor and roof, the minimum percentage reinforcement shall not be less than 0.35% for HYST bars, and shall not be less than 0.64% for mild steel. Okay. This is again the code is stating that if these values are very high, like 0.35% and 0.64% when we are comparing with the earlier code that we are using, IS 3370 part 2 1967, there it was only 0.3%. So this percentage can be further reduced to reduced if the dimensions of the tank are less than 15 meter, then it should not be less than 0.24% for HYST, and it should not be less than 0.4% for MyST. Okay, so this 0.35% and 0.64% can be further reduced to 0.24% and 0.4%. Also, if the wall thickness is less than 200 mm, so we have a tank, so this is the tank, this is the wall, okay, it's the floor and this is the wall. So if the wall thickness is less than 200 mm, we can provide the reinforcement. We need to provide only one layer of reinforcement. Okay, one layer of reinforcement is sufficient. This 0.35%, 0.24%, 0.4%, etc. Means the reinforcement in both directions. This is including the reinforcement in both directions. Okay, so if it is having 2 layers of reinforcement, then we will take half of this. Okay, so this is for two mutually perpendicular directions. Together it forms 0.3%. Okay. Again, the wall thickness we have discussed, like less than 200 mm, we have to provide only single layer of reinforcement, and if it is greater than 200 mm, then we can go for 2 layers of reinforcement. In case of floor slab, if it is less than 300 mm thickness, then we need to provide only 1 layer of reinforcement. Then the code also states the bar spacing. This is very important from point of view of crack prevention. The bar spacing shall not be greater than 300 mm nor greater than the thickness of the section, whatever thickness of the section, and whichever is small. That is very important. Whichever is small, that has to be taken. Then the code also specifies about the cover which we need to provide to the reinforcement, that is given in clause 6.2.1 of part 1 and there it says this can be based on the exposure conditions that we have already seen in our IS 456, normally using in our IS 456. The same value can be used over here in case of water tank also. So the next point that we need to discuss before going on to the design of tank is the behavior of circular tank with flexible as well as rigid joint. How these are behaving, how the circular tank is behaving when the joint between the wall and the floor, when the joint between the wall and the floor is flexible or it is rigid. Okay, so this is a water tank section that I am drawing. So it is having water. The hydrostatic pressure is acting on these walls. Okay, and due to this hydrostatic pressure, the wall is getting deflected like this, or it may be deflected like this. Okay. So This is the point A. This junction is marked as point B. This point is B1, and let this be C. Okay. So A, B, B1 is the deflected shape when it is a flexible joint. Okay. So this hydrostatic pressure is actually trying to increase the diameter of this water tank, So as this is a flexible joint, it tries to move from point B to point B1 as per the hydrostatic pressure. We know that hydrostatic pressure increases with depth. The maximum pressure will be at the bottom and minimum at the point A. So at the point A there will not be any pressure, and hence there will not be any movement. But the point B, it travels from B to B1. Okay, so this is the deflected shape for a flexible case. But for a rigid case, it will be A, B, C. For a rigid case, the rigid joint means the movement is restricted and there will be a bending moment, and the deflected shape will be then ACB. Okay, that is the deflected shape of the tank. And the water pressure, as we have discussed, the hydrostatic pressure will be maximum at the bottom, and that will be nothing but W into H. What is W? W is the specific unit weight of water that we know as 980 and 9,800 Newton per meter cube. Okay. Then then the next step is about the hoop tension in circular tank. The hoop tension in circular tank. The hoop tension in case of circular tank, this is a common term that we are going to see while designing these tanks, and we need to know what it is. The hoop tension, we have studied this particular thing in our mechanics of solids in S3. So consider this is a water tank, circular water tank, which is subjected to a pressure P from inside. Okay, from this inside of the tank, it is subjected to pressure P, and let the radius be R. Okay, so if I am cutting here, if I am taking a section over here, then the toe portion will be something like this. Okay, the top portion will be something like this, and where this much distance will be R and all. Okay, so we know that. If I am drawing the forces, the inside will be subjected to pressure force P. Okay, pressure force P, and thereby we have two components, which is Ft and Fr. Why this Ft and Fr like this? Because our pressure is like this, and the resisting force will be like this. If I am taking the component, I am getting Ft and Fr. Okay, so similarly at this point we are getting an Ft over here. This is the tangential component, and this is the radial component, which is Fr. Okay, so this is the free body diagram of that particular section. Okay, so we need to find out what is Ft and Fr. Ft is our actually hoop tension, and Fr is the radial force. Okay, so from the diagram itself, we know that from this, if I am giving them name, the point 1 and 2, from the point 1, the force is going outside, so it is a tension. That's why it's called hoop tension. These details all we have studied in our mechanics of solids. Okay, and based on the theory, or in order to maintain symmetry in the section, because if I'm taking the lower part of this circular portion, then the forces will be like here also Ft will be tension, but here the Fr will be, instead of compression, it will be tension. Okay, So there is a variation in the FR direction. At the top portion it is compressive in nature, but at the bottom portion it is tensile in nature. So if it is acting on that particular tank, the tank will get deflected like this. But we know that the tank cannot deflect like this because the upper portion is having a compression and the lower portion is having a tension. But we know that this is not possible. So the only possibility is that FR should be 0. Okay, in order to maintain symmetry of the cross section, FR should be 0, and the thing FT will only be not equal to 0. And we need to find out what is FT. And FT, if I'm taking a small element over here, and let this be delta theta, and let this be theta from X, and this be the Y direction. So this elemental arc length will be r delta theta, right? So the force, the radial component force, is delta Fr, that acting on that particular small element is nothing but P into the arc length, that is r delta theta. P into r delta theta, and that into this B. What is B? B is the, if I'm taking a three-dimensional structure, and this will be my width B. Okay, so this will be the force acting on that particular component, delta Fp. Okay, so the component in the y direction, if I'm taking the component in the y direction, because my Ft is in the y direction, so the component in y direction, delta Fy, is nothing but delta Fp sine theta, and what I'm getting is P r b sine theta delta theta. And if I'm taking the limits, delta theta tends to 0, then, and also taking sum of Fy equal to 0. So the two forces Ft are acting downwards. The vertical component of delta Fp is acting upward. So the summation from 0 to pi, if I'm taking the limits from 0 to pi, P r b sine theta, when delta theta tends to 0, it becomes d theta, and this is equal to 2ft. So this can be again written as, if I'm integrating sine theta and putting on the limits, I am getting, what I'm getting is Ft is equal to Pr into B. Okay, instead of going through this rigorous integration or something, if it is difficult, then we can also find out that the Ft will be the force on the projected area. Okay, the force on the projected area. From this figure itself, we can see that this is 2r. Okay, so the projected area will be nothing but 2r into B is the projected area, and that into pressure will give you the total force, and that is distributed at the two sections, right? So it will be 2, and Ft will be P into R into B. Okay, that is the hoop tension. So here, in case of our circular tanks, what the hoop tension that we are taking is Ft is equal to P into R into, instead of B, we will be taking 1. Why? Because we are considering for a unit height. So this will be, and we know that at the bottom the pressure is W into H. So our P is equal to W into H, and instead of R I can write D by 2. This is how we are getting Ft. The hoop tension is WHD by 2 at the bottom. So if I am taking any other section, suppose this value is H, small h, and this value is capital H, then I can get the value at this section by just Ft is equal to W into the total height minus the height from the bottom into D by 2. Okay, this will be we will be using this very very much in our design examples. Okay, we will see this equation again in the problems that we are going to solve in our next videos. Okay, thank you.